impulse functions. This is something that is very interesting. Direct impulse is something that looks like this. It's like a hammer hits a mass, and the mass immediately has a velocity and can move. It's a very fast. Something happens, something very large in magnitude happening in a very short amount of time. That's an impulse. The background, this is not a regular function. This is called a distribution. This is a generalized function. The background, at least one of the application, is as follows. We can imagine for step functions that look like this, it jumps from 0 to 1 at time 1, right? This function is not continuous. It doesn't have a derivative at time t equal to 0, strictly speaking, right? But in practice, a lot of cases, we still want to have this concept of taking a derivative of some signal that jumps. So how do we do? This is what we do. So we say, I can approximate this step function.
Hello, Professor?
Yes?
Can you unmute the wireless on the podium?
Can you hear me now?
No.
No?
Can you test it again?
Testing, testing.
Okay, it's good.
Okay.
Thank you.
Okay. This is a time varying system. Let's continue here. So we say it's good to be able to have a concept at least for derivative of a step function that looks like this. How do we do that? The way we do engineering is that we can do approximation. I can say, I can try to approximate this step function by this. Let me use a different color. I can do approximation that looks like this. It's exactly the same here, and then I'm going to not jump immediately, but have this sort of transient in between to go here. I can make this smaller and smaller, right? I can move more to the upper left. As this time here, let's say this tau, as this tau becomes smaller and smaller, I get a better approximation of a step function. But this new function, I can calculate the derivative in this range, right? I can calculate the derivative of so this is tau here. There's a smaller tau here, tau tilde. I can calculate the derivative perfectly fine in this range. So over here, it's a slope. It's a constant slope. So its derivative is constant. Let's say somehow it's like this. It has a derivative over here without problem. And then the derivative is 0 once we hit here, right? When tau becomes smaller and smaller, I still can do derivative. It's just this magnitude going to increase, right? As I go to the limit, I approximate the step function better and better by going to the top left. This is having this duration becomes shorter and shorter and then larger and larger in magnitude. In the extreme case, we get this. Effectively, we have a way of calculating the derivative of some function that has a jump. That's how the distribution, the delta impulse, becomes helpful.